This is the first of two videos in which I'm going to review and explain Gauss's law. Gauss's law is extremely important in electrostatics. In a way, it's at the basis of it all. And from my experience, it takes some time to get your head around it. Like, what is it saying? How do you apply it? And so on. But once you have a few examples under your belt, you'll see how powerful it is, and you'll never want to get rid of it again. So in this first part, in this first video, I'm going to cover the background we need. Specifically, I'm going to introduce the notion of electric flux. And then I'm going to derive Gauss's law. When I say derive, I'm not going to do a mathematically rigorous derivation, but I'm going to argue, starting with Coulomb's law, why Gauss's law should hold. Okay, so why bother with Gauss's law? Well, there are two reasons. The first one is essentially it's a calculation tool, and the key usage it has, it allows us to avoid those cumbersome integrations that you were struggling with in chapter 23. Gauss's law is chapter 24. So the integration, for example, that was involved in finding the electric field due to an infinite sheet, or the electric field due to a long rod, or something like that. Right? Those kinds of calculations where we had an integration, well, we can do them faster and easier once we've got Gauss's law. So it's a calculation tool. But also, it's just one of the fundamental laws of electromagnetism. And you say, but what about Coulomb's law? Well, Coulomb's law is really a special case of Gauss's law. Namely, what you get Coulomb's law back when you apply Gauss's law to a point charge. Or more generally, when you apply it to any sort of spherically symmetric setup to some extent. So Gauss's law is more general, it's more powerful than Coulomb's law, and we can essentially forget about Coulomb's law once we have Gauss's law, because we can always get back to it by just applying Gauss's law to, say, a point particle. Okay, so the first piece of background that we need is we need to talk about flux, the notion of electric flux. The second piece we're going to need is the notion of field lines, the field line representation of the electric field. Now, I hope you've read about it in the book, maybe watched some other videos of it, but just in case you're wondering what we need. We need the field line representation. That is essentially the electric field is not, like a bunch of tiny vectors, or not drawn as a bunch of tiny vectors, but essentially a sort of continuous lines, something like this. If you've seen those kinds of pictures, you can interpret them for the electric field, then you have what it takes to make sense of Gauss's law. Second thing we're going to need is the notion of electric flux. And just to come back to this, if you're unsure about this, the relevant pages in the book are 634 to 635. It's just a quick section, so feel free to just pause the video and read this, or reread this before you continue. The thing we're going to talk about right now is this idea of electric flux, and that is in section 24.3. 24.4 in the book, we're going to derive Gauss's law. We ask what about 24.1 and 24.2. Well, those are about symmetry, because we're going to need a lot of symmetry reasoning. We're going to need to reason with exploiting symmetries when we apply Gauss's law. And we're going to do that just as we go along. By 24.3 is where the concept of electric flux is introduced. That's what we're going to do right now. So the concept of electric flux, or let's start with flux in general. I'm not going to attempt right now a technical definition. We're going to come to that. Instead, I want you to get a sense of what it means, right? The point of these videos is to help you understand, not to just provide you with facts. So, what is flux? Flux is essentially how much of something goes through some surface. I'm going to start with an example that has nothing to do with electrostatics. I want you to imagine the following idea. Imagine there's a wind blowing. This is the direction of the wind. And now imagine you've got a window frame. Right, so this is wind. I can imagine this wind, there's it's blowing with some velocity. Let's call it V air, right? Now imagine you have a window frame. So, just you hold in your hand a window frame, and we want to know how much air is going through that window frame. Now I'm going to have to try to draw this in 3D, which is kind of difficult. But you can imagine maybe for the window frame that sort of looks something like this. Right, this is my attempt of drawing in 3D. You can see that's the best I can do. Let me annotate it in case you're wondering later what is that weird squiggle. Window frame, right? So we want to figure out, well, how much air is going through the window frame every second. That's what we mean by flux. Flux, in this case for airflow, is the volume of air that's going through our window frame every second. Now, what factors does this depend on? The first thing that it depends on is the size of our window. Right? The bigger the window frame, the more air is going to go through it. Everything else staying the same. Makes sense. The next thing that's going to change the amount of air that goes through our window every second is how fast the wind is blowing. Right? If the wind was not blowing at all at 0 speed, then no air would go through it. It would just sit there. The way to sort of make sense of this, imagine that you want to ask, well, what air is going to go through the window in the next second? Well, the way you might do this is you might sort of imagine a box, something like this, and I'm going to continue to try to draw this in 3D. You can imagine a sort of box like this that's sticking out from the window frame. And then if the air goes with, say, 2 meters per second, well, if this box is 2 meters long, right, then this back area of this cube of, or this cuboid of air, that is what's just going to make it through the window. So everything inside this this volume is going to go through the window. And so in that case, the volume of air would be the area of this times the length of this. But the length of this, well, that is just the speed, right? Again, if the air is going 2 meters per second, then this has to be 2 meters long, so that everything inside it is just going to make it through the window in the next second. The bit of air that's over here, just to the left of it, is not quite going to get there in the first second. The bit that's to the right of it, like inside the box, well, that's going to go through it, at 0.9 seconds, it will have made it through the window. And what's on this sort of back panel of this box, that's just going to reach the window at the end of a second. Right, so the flux in this case is going to be the area of the window spelling is difficult. The area of the window, the frame, times the speed of the air. The amount of stuff going through something. In this case, the amount of air going through our window frame. But that's not the whole story, right? Because in this assumption we made here is that the window is really facing the wind. Let me draw this from the side. So here's my airflow. If you imagined I was holding the window like this. This is kind of my side view of the window, right? I'm looking at this window just from the side, so I can only see this edge here. My side view. Right, that was the situation above. But now imagine instead you have a situation with the same window, but you hold it at an angle. Same window, same size. Now I hold it at an angle like this, with the air still flowing like this. It's going to go through the window, but the air up here isn't going to make it through the window frame, right? Up here, although the air, all those three flow lines made it through the window. Here, that is no longer true. Now, can you imagine the sort of bigger the angle this is tilted, right, the less air is going to get through it. And if you look at the geometry of it, it's almost like we've reduced the window size from this to a sort of an effective window size of this. Right, this, any air that goes through this imaginary little window is going to make it to the actual window. So in a sense, this is a component of this. Now, how can we quantify this? Well, the nice way to do this, the easiest way to do this, is imagine our window has a little flag that's sort of sticking out of it like this. Right? If the flag and the velocity of the air are parallel to each other, then we get the full area times the speed. If they're at an angle, then, well, the angle between the direction of the airflow and the flag, called as theta, that angle is just the same angle by which we've tilted our window. You can just look at the geometry of this, or you can imagine you just start at 0, then they extend the angle, the angle between the flag and the flow line is 0. If the window is the way my pencil is now, then as I tilt by 1 degree, okay, now the flag has 1 degree with the flow line. So the flag has 2 degrees with the flow lines, 3 degrees, and so on. I can imagine this like tilting this with the flag sitting out like this. So this is the adjacent to this angle. So the actual flux, the actual thing we're going to have to add up here, right, from this, so you have to add a factor cosine theta, where theta is the angle between the flag and the flow line. Okay, now let's rewrite this in a somewhat more convenient way. So I've got that the flux is the area, let's call it A, times the speed of the air times the cosine of the angle between the flagpole and the velocity vector. So I'm just going to write down how to make this more concise, and I'm going to explain it. I'm going to write this as A as a vector dot product with the vector that is the air. Now, hopefully you remember the dot product of two vectors. Dot product just going to give you the magnitude of one times the magnitude of the other times the cosine of the angle between them. How to calculate that with components? Well, you might want to just go back and to your math notes and look that up, or alternatively find a quick video online that explains that. Right, but this is just a more compact way of essentially writing this. But this is just the actual magnitude of the area. How big is the area? What's the speed? what's the angle between this flag and the flow line. So what this is clear, right? This is just the velocity of the air. Velocity, speed, and direction. But what about this one? Well, if you have an area as a vector, what we mean by that is the magnitude of it is just the area. So we can write this out. The magnitude of this vector is the literal area, and the direction of A, that is the flag. Right? As I said, this is not a formal definition. There's no real flag, of course, but you know what I mean, and that is the point of this video. Okay, so this is going to be our expression for the flux. Right, so make sure you understand that before moving on. Okay, but there might be a situation where our airflow isn't nice and uniform like in what it was in those cases here. Right here, the air is flowing nicely sideways, the same everywhere, no change at all. So we could imagine a situation where instead we have air that might be flowing something like this. And maybe it's flowing at different speeds in different places. Now I can have my window frame, at some orientation, at some angle, somewhere. Again, I'm going to do a sort of side view. Maybe it's here. Now at different points, maybe we should draw a couple more flow lines. At different points along the window, the air is going to hit it at a different angle and possibly different speed. Write this out. Different angle. By angle, I mean the angle between my imagined flagpole. Now I might imagine there's one flagpole here, another one here, right? All the same direction. But the angle between the flagpole and the flow line isn't quite the same in different areas along different parts of the window. So different angle and different speeds. So what can I do? Well, the trick is I'm just going to split my window into a lot of tiny windows. So that I've got a tiny window here, tiny window here, tiny window here, and so on. And for each one, if I make them small enough, the airflow through that, or the air velocity through that, is going to be a constant. It doesn't change much just because I'm maybe looking at lots of tiny windows, and from here to here, the difference is utterly negligible. Right, so we split it into tiny windows. Right, so my big window looks like this. It's my window frame again. We want to split it up into a bunch of tiny chunks, kind of like a mosaic, right? It's a glass mosaic, except for air to go through it, there's no glass. But you get the idea. We're going to split up in lots of tiny areas. Let's call those delta A. Lots of tiny delta A, right? Lots of tiny areas. Use delta to mean small little chunks. They add up to make the whole area of the window. And then the flux, so the whole window, is just going to be the sum of all the individual fluxes. Not sure if that's the right plural here. Maybe flux doesn't have a plural. But you understand what I mean, right? Sum of all individual fluxes, each one being delta A, Right? Each one little window has its own little flagpole sticking out of it, times the air speed at that point. And of course, for each one, right, I'm going to pick the air velocity vector at that point, at that point, at that point, and then I add them up. And you can, if you've been paying attention to this course, you can imagine what the next step is. Well, if we add up a very large number of tiny, tiny bits, and if you imagine we make the bits infinitesimally small, then we're going to end up with an integral, right? A sum of infinitely many infinitesimally small bits. And so what we find is the total flux is equal to the sum, right? The sum. And we're going to sum up over the whole window. And you can take our sum until we've summed up the entire, and we end up with the entire window of dA, and I'm going to turn my delta into a d because I'm imagining I'm going to the infinitesimally small. It's not just small, it's not like 1 square millimeter at a time, it's 1 square infinitesimal meter at a time. Dot v air. Right, if I work this out, maybe I've got some function for this, and I know what this is. In the case of a flat window, this would be constant. I could work this out, maybe analytically. If I can't do it analytically, maybe could I plug into a computer and go back to having lots of tiny chunks. That's beside the point, right? This is the expression we're going to have for the flux in the case of air going through a window. Now, we don't talk about air in this course. We're going to talk about the electric field. But the idea is exactly the same, and you probably already guessed that given how I was drawing those flow lines. So we're going to define the electric flux through an area A, so you might say through a surface. Let me replace this with the word surface. A is going to be phi subscript E, E for electric. We're going to meet magnetic flux later. Phi, this is a capital Phi, the Greek, the Greek letter that sort of makes an F sound, kind of like our F. That is equal to the integral, meaning the sum, until we've summed up over the whole area of the flux of each individual bit, but now the flux is, well, we're working with the electric field, and the visualization would be electric field lines. Electric field lines don't really flow, right? There's nothing flowing along a field line. So it's not like air, nothing is moving along the field line. But mathematically, it's still the same idea. And I think the visualization with a flow of air, say, can help. So let me just annotate this again. This part is the flux through the infinitesimally small area piece mosaic area or a little surface piece, right? One of those tiny little squares. Right, so this part is just the flux through one of those pieces, whatever the electric field is at the point where the piece is, times the area of the piece, taking into account the angle, right? So I could write this as dA dot times magnitude of E times the cosine between them. That's what a dot product means. Again, if that's already confusing, then just go back in the video a little bit. So now I want to sum all those up. That's what I'm doing by taking the integral. Okay. So we have now, excuse me, we have now covered the concept of flux. And specifically, we've got the notion of electric flux. One thing to note is that our window does not have to be a flat surface, right? We could have it curved, and what that would change is that the flags sticking out of it, or can you imagine lots of little flags sticking out of it, they wouldn't be parallel to each other as you move from one place on the window to another. Right? So if our window had a shape like this, say, but imagine the flag here looks like this, the flag here looks like this, the flag here looks like this, but they're all with 90 degrees to the window. It's a curved surface. Right, the notion of flux, again, is exactly the same. Okay, so now we've got this concept down. Make sure you understand this before we move on, because we're going to be using it. Now let's go to the simplest example of an electric field that's not boring, which is electric field due to a point charge. Here's my point charge, and the electric field. The field line representation looks like this. Right, field lines start on positive charges and on negative charges, and if there's no charge nearby, they just keep going. They never cross. Right, all that stuff. Again, the pages in the book were, I think, 634 to 635, as I said in the earlier part of the video. So now let's imagine, right, I'm going to put a ball, you're going to think in 3D here, we're going to put a ball around this charge. Now the charge is meant to be right in the center of the ball. This is poorly drawn, I do realize that. And the radius of this ball is r. And perhaps I should use more colors here to make clear what I mean. So this thing here is a sphere, a closed sphere of radius r centered on the charge. Now, the question is this, what is the flux through that sphere? And I want to emphasize by sphere, right, when we use sphere in, say, math or physics, we don't mean the ball including the inside, we mean just this shell. Right? If this were some kind of ball that's filled with air, we don't mean the air, we just mean the rubber on the outside. Something like that. Okay. So what is the flux through this surface? Well, we look at this, and one thing that's convenient here is that while the surface itself is curved, and therefore the flag keeps changing direction, right? The flag of the surface might be sticking out like this, sticking out like this, sticking out like this. While the flag keeps changing direction, what we notice is that the field lines, the electric field, is always parallel to the flags. So E is always parallel to any little tiny chunk of area here, or every little tiny chunk of area here. Wherever I look on this sphere, the field lines just point straight out of the surface. Not at some funny angle, right? Just, it's always 90 degrees, 90 degrees. So they're exactly parallel to the flag. That means that calculating the flux through any one of those little pieces is going to be easy, because we also know what the strength of the electric field is. So the second thing we know is that the E field, well, we know what it is, a distance r away from a charge. It's equal to k times q, whatever the charge is. And I assume it's a positive charge, but it might as well have been a negative one. Right? And you just get a negative well, the field lines just change directions over r squared. So what that implies is that the flux through a single tiny piece of our mosaic that's covering the sphere is, well, it's E times the area size itself. You write it like this. Right, times the size. The magnitude, remember, of an area is just of an area vector is just the size of this little, like 1 square micrometer. That's what this is. Times cosine of the angle between them. But the angle between them, right, is 0. And so the cosine is just 1. Cosine of 0 is 1. And we know what the electric field is, right? Which means this expression for the flux, let me move my pages up, the expression for the flux is going to be K Q over r squared times dA, the size of the little area chunk, times 1. Okay, so that is the flux through the tiny little, little piece of the area that's making up the sphere. Write this down, flux through one piece of the surface. When I say piece, I mean infinitesimally small piece. The surface here is the sphere. So now we want to add them up to get the total. Right? Now add up to get the total flux. So we're adding them up, but lucky for us, this thing is the same for every single tiny piece, right? So really what I have is the total electric flux for the surface is the integral over the total sphere, meaning, we're summing up the tiny pieces until we've made up the whole sphere, of E dot dA, or the A dot E is the same thing, which I now know is sum over the sphere of kq over r squared times just the area itself. This whole thing is the same for each one, so I can just take this out the front of the integral. I'm summing up the, oops, that was not what I want to write, excuse me. I was going to take the kq over r squared out times the integral over the whole sphere. We were just adding up the areas. Well, what is that? If I just take the size of each tiny piece of the sphere puzzle, right? Each tiny little piece of area, and don't multiply it by anything. I'm just going to add them all up until I've got the whole sphere. Well, that means this whole thing here, that is just the surface area of the sphere, right? If I'm adding up tiny pieces, and my condition is I'm adding until I've built the whole sphere, but all I'm adding up is the area of each one. I just get the total area in the end. So we're sort of doing an integral here, but it's an easy one. We don't really have to work anything out. We're just saying the sum of all the tiny chunks, taking the sum, keep adding until you've got the whole thing. That's just the area of the whole thing. It's almost a trivial statement. So the area of a sphere is 4 pi r squared. Right? So what I'm getting is that the total flux phi e through our sphere is going to be equal to kq over r squared times 4 pi r squared, right? This is our surface area of the sphere. This is the magnitude of the electric field. The cosine between them was 1 everywhere, so I don't have to worry about that. What you notice is that the r squared is going to cancel out, and I'm going to get 4 pi kq. And at this point, you can see why we might get away from the k, because what you hopefully remember is that k can be rewritten as 1 over 4 pi epsilon 0, and so that means this thing here can just be written as q over epsilon 0, where q is the charge inside. Notice the answer is independent of the size of sphere that we picked, right? I didn't make any assumption about what r is. It's just some value, some radius. Well, it turns out our answer doesn't depend in any way on the radius we picked. And now if you think back to the field line picture, that makes sense, right? Any field line is going to go out of the sphere at one point or another, no matter how big the sphere is. If the sphere is smaller, the field lines are denser, and they're going to come out, more of them are going to come out in a small, over a small area. If the sphere is bigger, they're further apart, or the electric field is weaker, but there's also more total area. And that sort of compensates, right? Any field line that starts on the inside at some point leaves the sphere, so the number of field lines leaving the sphere, the number of field lines passing through the surface, and that is just what we mean by the flux, that stays the same no matter the size of the sphere. Okay, so that's for a sphere, right, with a charge at the center. Now, imagine though, instead of having, say, a sphere of one radius or another, imagine instead I have a positive charge here, and then instead of creating a sphere around it, I want to create sort of two half spheres around it. You've got to think 3D. Imagine I take two spheres, one small, one large, and I'm going to cut them in half, and I'm going to stick them together like this, have a sort of flat surface here. What's the total flux through that one? Well, this is going to have half the flux that we had up there, because it's half a sphere, and the whole thing is symmetrical. Take a sort of hemisphere, and in this one, same thing is true. If I draw field lines, they look something like this. Again, the number of field lines passing through the surface in total is the same as before. The flux through this is half of that, because it's half the sphere. The flux of this is half through that, because it's half the sphere. So they add up to the same, and there's no flux through those, because in these cases, the flag sort of sticks out sideways, and it's perpendicular to the direction of the field lines. It's kind of the situation where we hold our window like this, and the air just blows over the top of it, and nothing goes through it. So this has the same total flux. Now imagine, of course, flux L in there. So now imagine we can change up our shape some more. Imagine I have my positive charge here, and I'm gonna say I'm gonna have a little bit of a sphere here. Then I'm gonna maybe build it like this. Then I'm going to go out, have a larger chunk here, go like this. Maybe I'll then have a tiny little thin area here. Right? Poorly drawn. Excuse me. This should all be sort of radially outwards, I guess. Right. Get the idea. Just imagine I have a sort of different sizes of pieces that I'm putting together. Let me just draw this again. This is awfully drawn, right? Awful picture. Don't look at it. Draw it again, right? So imagine that maybe there's part of the area here, then part of it is here, then maybe this goes out like this, and then over here it goes out like this. Maybe I'll just leave it something like this. How about we go with this shape, right? So it's sort of just these different chunks of a sphere. Of course, again, if you think I do this in 3 dimensions, but I can't draw this. If this is a quarter of the sphere, well, it's going to have a quarter of the flux from what we had before. Quarter of this. If this is 1/8 of the sphere, it's going to have 1/8 of this. Because I'm surrounding the whole sphere again, the total flux again is the same. Right, the same total flux, because it's just I'm piecing together different spheres, but in a way that they make up a closed surface again overall. As I said, I'm not doing a mathematically rigorous derivation here. This is just to give you the idea. And the second idea here is how to understand this is, well, all the field lines, same number of field lines, come out of this as before, and they all go through exactly the surface exactly once. If I imagine I build my sphere up from an infinite number of utterly tiny such segments, I could essentially imagine I just have some sort of shape around it. Again, imagine it's a 3D closed surface, no holes in it, right, but it's sort of hollow on the inside. The number of field lines going through this is going to be the same. And so then let's state Gauss's law. Gauss's law then states that the flux, the total flux, through a closed surface, and it has to be closed, no holes, right? If there are holes, the field lines might sort of escape and not get counted. Not go like the wind might not fall through the window, it might just sort of go around it. So it has to be a closed surface. That is equal to the charge inside. Like inside our closed surface, right? If you can imagine this, hollow ball, or maybe you put some dents into the ball, but it's still closed, right? You can't sort of peek in what's inside. So charge is inside, it can't get out. There's no way to get it out. Divided by epsilon 0. Or if I want to write this as an equation, I can write this. Integral over a closed surface, E dot dA is equal to Q inside divided by epsilon 0. That is Gauss's law. Sometimes you see this written as a sort of double integral because it's an area integral. Sometimes you see a little sort of symbol like this, meaning it's a sort of emphasizing, look, this is a closed domain of integration, but it really doesn't matter. The notation here is less important than the understanding of what it's saying, right? If you just have a normal integral over the closed surface, totally fine. Okay, now you might say, hold on, okay, I understand all those sort of 3D pizza slices, how they make up the whole sphere, how the flux is the same. But what if I have more than one charge on the inside? Maybe there's a charge here and another charge sitting somewhere else. Well, that's okay, because if you have electric field due to more than one charge, so more than one charge is contributing to the electric field in the vicinity, then the electric fields add. If electric fields add, that means the fluxes add. More than one charge, right? E total is the electric field due to each charge, say if there are two, the contribution to the electric field due to each charge, and that implies that E total dot dA, the flux through a tiny little bit, is E 1 dot dA plus E2 dot dA, and so the total flux, electric flux, is just the electric flux due to the first one plus the electric flux due to the second one, you know, as if the second one wasn't there, as if the first one wasn't there. And so you get this same thing back, and you just, you know, you have it for each individual charge that's inside. Well, then you just add the left-hand side, the total flux is equal to total charge inside over epsilon naught. And if there's the same number of pluses and minuses on the inside, this might be 0. That'll tell you something about the electric field. But this statement here, right, this is Gauss's law. Let me put a giant box around it. Right, this is Gauss's law. How to apply it? Why is it so powerful? How can I do calculations with it? And how does it give me back Coulomb's law, like I claimed at the beginning? I'm going to discuss that in the second part, in the second video, that you should be able to watch right after this one.